Hey everyone, how's it going? Welcome back to 4300. Today we've got a really cool lecture. At least it's one of my favorites. I hope you enjoy it as well. So I saw that I think I had 21 submissions for the project proposal. And so that's good. I think that's pretty much all the groups. I haven't heard any real complaints or excuses from people for not submitting on time. So I'll be looking over the project proposals this weekend and getting feedback to you on that as soon as possible. If you don't hear any specific feedback, it means it's fine. So if you just get the marks for your project proposal and nothing else is there, then you don't have anything to worry about. I think your game idea is great. Today we're going to be talking about memory pooling and profiling and optimizations. And this is one of my favorite topics in all of computer science, not just in game programming. And so let's hop into that because I think it's going to be really interesting. Okay, let's go over to the PowerPoint. Okay, so as I just said, this is lecture 19. Wow, we're almost up to the 20th lecture. We're going to be talking about game performance, memory pooling, and CPU caching, and how that all ties in together so that you can take your game and make it as fast as possible. Just give me 1 second here. So game performance. There's many factors that determine the overall performance of our game, right? There's lots of different things. With entity component systems, we can profile our systems independently and determine which are bottlenecking the program's speed. So for example, typical bottlenecks could be physics, AI, rendering, raycasting, etc., etc. And so in many IDEs, for example, in Visual Studio, there are actual profiling tools available that let us see exactly how much time was taken in each function. And if I have time at the end of the lecture, I'll go back and open up Visual Studio and do a profiling trace of say, one of our assignments so we can see how this works. So here's one example here where you actually get printed out for you this tree of basically a stack trace of the tree to see how much time was spent in each function of the program. So here's another view of this from another visualizer where you could say, okay, for example, here is my how much time my rendering function took, and within that rendering function there are other functions such as draw or render scene. You could see how much time the CPU took versus the GPU took, and so there are a lot of great profiling tools out there for you to be able to deep dive into your program and see what are the bottlenecks and what aren't the bottlenecks. And so I've included here, I'm not going to go into all of those topics because there are really great resources available online for that. So for example, visual benchmarking in C++, manual tools for profiling and visualization. This video right here, the first one, is absolutely excellent and I highly recommend it. Debugger diagnostics in VS 2019. So we're using Visual Studio for the course, or at least those of us who are using Windows. And so this video here, as well as tuning C++, benchmarks, CPUs, and compilers, these videos are all great to help you with trying to debug the performance of your program. And one of the really great things about ECS is that you can turn on or off individual systems, right? So just think about how easy it would be to say turn off the rendering or the graphics in our program. Well, all we have to do is turn off the call to the render function. And then we could run our program and see, okay, if rendering weren't the bottleneck, then what is the bottleneck? Or we could turn off the collisions or turn off the movement or something like that and profile each function individually. So that's one of the hidden benefits of entity component systems, is not only that is ECS easier to program, but it's also easier to debug and it's easier to profile as well. Okay. So let's talk about some non-obvious performance hits that performance hits that you could get in your programs. So it's easy to think that the only things that affect performance are algorithms and mathematics, right? So this is true. For example, if you have an algorithm that takes like big O of n squared, and you change that algorithm to be log of n, then you're going to save lots of time, right? There's no denying that changing your algorithms to be more efficient is going to save you time. However, in practice, oftentimes the implementation of conceptually simple things can impact performance just as much or even more than those things, okay? So what you've been taught in computer science up to this point, and even though this is a fourth-year course, you've probably been told that running time means big O notation, right? So you've got some input size n, and you're going to analyze your program, and you're going to say, okay, big O of n squared versus big O of n, or big O of log of n, and you're going to do that sort of theoretical analysis of your program. However, in practice, if you have, say, small or medium size inputs for n squared, then if you have a very slow implementation of that algorithm that's n squared, if you have a very slow implementation of a linear time algorithm versus a very fast implementation of an n squared algorithm, then your n squared algorithm may actually run faster in the program, okay? So there's this real difference, there's a trade-off between theoretical performance and practical performance, and we'll see what we mean by that in this lecture. So, here are important optimizations that I would consider for your program. And yes, first and foremost, use more efficient algorithms, right? If you're trying to sort an array and you're using an n squared algorithm, try looking up an n log n algorithm for that. It will definitely save time. However, depending on your implementation, and we'll see the details of this later, it may not save you time. So using more efficient algorithms, this is where computer science really helps. So again, you're almost at the end of your computer science degrees, and probably what you've realized by now was that a computer science degree is not a programming degree. It is not a software engineering degree. Computer science is, despite what people think, it's more mathematics than it is programming, okay? So using more efficient algorithms is kind of where, that's where computer science really, really helps you, is theoretically. But that's also kind of where computer science stops helping you, right? Because at least when I did a computer science degree, I never learned anything about like practical implementations of real-world optimizations. None of that was important enough to go into a computer science course. But you're going to learn some of it at least in this course. So here's one thing you can do. Minimizing the size of data structures, and I'll go into some examples of that. There's code reuse and modularity. There's minimizing dynamic heap allocations, and we'll talk about this and how we implement this via memory pooling. And also writing cache-friendly code. So we can do data-oriented design and programming in order to help us with this. And so computer science really only teaches you this first one, right? Maybe a bit of the second one. But in terms of like real-world practical applications, these last two can save you as much or even more time as the first two. Okay. Minimizing data structure size. Why would we want to do that? Well, so first of all, C++ gives us really fine control over the size of data structures that we can use for our games. Deciding on the size of a type for your data depends entirely on the context for your game, your function, your structure, etc. And minimizing data structure size can help your game in several ways. So it's not just the obvious, hey, we're going to save more memory. It could also speed things up in other ways. So here's the ways that it can do that. So if you reduce your data structure size, it's going to use less memory. Okay, so the obvious benefit there is less RAM usage. You've got, so many gigabytes of RAM, you can maybe cut that in half by using shorts instead of ints or something like that. However, the secondary benefit is that the reduced size in your data can also lead to less time in copying your data. So if your data needs to be copied in your program, this can dramatically time. Well, that's obviously a typo. It can dramatically reduce the amount of time that it takes. So for example, if you've got data stored in a vector and you add something to the vector and the vector has to resize, then that's copying a bunch of data. So if your data is smaller, then that takes less time as well. And not only that, but if you can get the size of your data structures to be less than or equal to 8 bytes, then you can pass them by value instead of by reference. And if you can do that, then you can eliminate the dereference on a function call, and you can eliminate a potential cache miss on function calls, okay? And we'll talk about cache misses in a little bit. So let's look at an example of data size. Let's say, and if you did 3200 with me, you're probably getting PTSD right now looking at this, but don't worry. So let's say we have a game world, and this is our game world map, okay? And this right now is of size 64 by 64. Well, if that's the size of our game world, we don't need to store a position using a full integer, for example, for the player location. So if we know that the player's location is going to be between 0 and 63 in the X and 0 and 63 in the Y, well, a full 32-bit integer, we don't need, that's too much information, right? Yes, we could store it in an integer, but why don't we use something smaller to try and use less data? So for example, why not try an unsigned char? Okay, so a char is 8 bits. Unsigned char can have values between 0 and 255. So if our world size, if we know it's going to be between 0 and 63 or 0 and 64, whatever, 0 and 63, so 64 possible values, then an unsigned char is perfectly fine because it stores 256 possible values. So that's one way that we could optimize the data size, is by not having to store full integers when we don't have to. But be very careful when you're making optimizations like this. Don't prematurely optimize things. Because, for example, if we thought that the biggest world was going to be 64 by 64, but later, and then so we come in and we change all our ints to unsigned chars, and now we have this really efficient data structure. But then later on, we decide, oh, the game designer wanted to have one really big map. And so they wanted one really big map that was like 512 by 512, and now we can, and everything breaks because we can't store 512 possible values in an unsigned char, okay? So the important key here is not to do premature optimization. So once your program works, then you go back and optimize it, okay? This is very important. You want to get things up and running. You want to be iterating on your design and your programming and your implementation, and then only when the designers say, okay, we will definitely not have any maps that are bigger than 256 by 256, then you go back and optimize things, okay? Now, that's not to say that you always want to do this, right? It's probably the case that if you're working with ints, it's going to be the exact same running speed as if you were working with chars anyway, okay? And that's to do with the way that, okay, for example, if you pass a char into a function, it's actually passing 4 bytes or 32 bits anyway. So this is just an example of an optimization. It's not necessarily one that you would want to do all the time, okay? Okay, next comes code reuse and modularity. And we've talked about this before, and ECS does a really great job of having code reuse and modularity. And so the key here is that any time in your program that you have code that is written twice, then you probably want to have a function for that code, okay? So if you, for example, if you need to sort a vector somewhere, well, if you just implement the sorting code right in another function, and then somewhere else you want to sort a vector and you rewrite the sorting code, then you probably want to have a function that does sorting that you can just call, okay? So not only does this like reduce the mental strain by having more code reuse and more modular functions, but what it means now is that if you have one function that's being called in multiple places, then you only have to optimize your code in one place, right? So for example, even if you just had 3 or 4 instances of the same code reuse, you would have to go and optimize that code in each of the different places that you used it. And so by putting it into a function, you can optimize the hell out of that function later, and you know that anything calling that function is going to be optimized. Okay? So even in cases where you think it might be overkill to use a function, sometimes it's good to use a function because then you could do things like optimizing that function. Not only for optimization purposes, but also for debugging purposes as well. So let's take, for example, let's say I just had some data structure like a vector, and I wanted to like get and set things to the vector, right? So you could just call the vector directly, right? You could just say, okay, give me the thing at this location, set the thing at this location. One example would be, okay, let's try putting a function to get things from the vector, or a function to set things in the vector. And then what you could do with that is that you could do some bookkeeping, and you could keep track of, for example, how many times you're writing to the vector and how many times you're reading from the vector. And then you could use that to benchmark and profile and optimize your code. Now, that's not saying that you would always want to have the overhead of a function that looks up something in a vector, but sometimes it could be useful to do something like that. And the example in our ECS for our course is the entity manager, right? So we use the entity manager all the time. And the great thing about it is we don't have to know how it works whenever we're using it, right? So we just say entity manager.add entity, and we give it a tag. And the person calling that function might not even know how the entity manager works under the hood. But the person who's in charge of the entity manager on the project could be optimizing that function all the time and making it faster and faster without the people who are using entity manager even knowing that that's going on. Okay, that maybe they could have a set there, or a vector, or a dictionary, or whatever ends up being the fastest for your use case. And by having this be modular and inside function calls, the person who's calling that function doesn't need to know, and the person who's maintaining the function can be optimizing it more and more. And so any optimizations that we make inside that function don't require any top-level changes, right? They are specific to that function, and that's just, it's a really nice thing to have. Okay. The next topic is minimizing dynamic memory allocations. So we talked about this before. So remember that static memory lives on the stack and dynamic memory lives on the heap. And we showed how that whenever you want to make a dynamic or non-fixed memory size structure like a vector or whatever, this is going to require calling the heap. And we do this in C++ with the new keyword. But what this does, so what C++ does when you allocate a heap allocated structure is it calls the function malloc, or memory allocate, underneath, okay? So if you call like my class C equals new my class, that new keyword uses malloc to, that's a C function, to allocate that memory and give us a pointer to that memory. But how malloc actually works is operating system dependent, okay? So each operating system is going to have a number of things that it does in order to try and find you a contiguous block of memory of a given size. And so what a contiguous block of memory is that whenever you want to store data in memory, like a vector or an array or your class or whatever you're putting into the heap, the operating system has to go through your RAM and find an uninterrupted part of RAM. So for example, if you have a 1 megabyte vector that you're trying to allocate, or a 1 megabyte data structure, malloc has to actually go through your memory and find 1 megabyte of continuous memory addresses that are not being used by anything else on your system. And given the complexities of how your memory is laid out and the fact that your operating system is using some memory, some of it's reserved, some other programs are running, etc., dynamic memory allocations can be very slow. And I managed to find this diagram. So this diagram, if you look here up in the top left, this is the logic flow of malloc, I believe, on Linux. Okay? So this is the logic flow diagram of what happens every time you make a dynamic memory allocation in C++. It's not trivial, right? This is a function which does a lot of things, a lot of system calls, a lot of checks to memory. It is slow. We want to avoid this at all possible. And not only that, but look, even just freeing the memory has its own bunch of stuff that happens, okay? So I've linked up here to, I know you can't see it because of my my current let me actually just post this in the chat. Let me see if I can do this. No, I won't do that. But it's in the slides, okay? So you can pause that and type it in if you want. Also, there's reallocate. And so if you want to reallocate something, that's also expensive. The point being here that without going into any of these like really fine details, dynamic memory allocations are very expensive and we want to eliminate them if at all possible, okay? Let me show you an example of why this matters. Here is an optimized version of assignment 3 that I wrote. This is capable of generating and rendering over 60,000 entities per second. Okay? And this is because this version of the program has 0 dynamic memory allocations. And by the end of the lecture, you'll know how to do this. But it's kind of crazy, right? Like, we're not using any crazy algorithms or anything like that from computer science. This is all implementation specific stuff. And if you think about it, if we were to do this naively using our current system for ECS, each of these bullets that I shoot is going to create a new shared pointer to an entity, which is a dynamic memory allocation. So for each of these, like, I don't know, however many tens of thousands of bullets per second, the operating system is calling this function. And then after the lifespan is done, the operating system is calling this function to then free it. Okay? So we want to eliminate any calls to dynamic memory allocation during the runtime of our game, if that is possible. So let's talk about how that might be possible. Memory pooling. Memory pooling is awesome. And memory pooling is exactly what you might think of it as. It's a giant pool of memory. So, heap memory is slower to allocate than stack memory. Oh, hey, I got a bunch of trolls in the chat. Let me ban these people real quick. Where's Nightbot? Nightbot is sleeping. There we go. Tossing out a few bans. All right, if I banned anyone by accident that wasn't supposed to be banned, let me know on Discord. Okay, so heap memory is really slow to allocate. Stack memory is really fast, but it's too limited, okay? Stack memory, we just have a few megabytes, and so, you know, any interesting game we're writing is going to use more than a couple of megabytes of memory. So what we could do is let's allocate a large chunk of heap memory at the start of our program, and then we'll use only that space for the memory of the lifetime of the program, okay? Now, allocating and deallocating heap memory is slow, but accessing the memory is no different than accessing the stack memory, okay? Now, within the context of cache hits and cache misses, which we'll talk about. So what we're going to do is we're going to, at the start of the program, allocate a big chunk of memory, and then we're going to operate within that memory for the lifetime of the program. And this is going to eliminate the need for allocations during runtime. However, this is going to add the complexity of managing the memory pool and managing like where we put the objects and stuff. And the other downside of this is that whereas before we didn't have a memory pool, the memory allocations were slower, but we allocated memory as we went, right? In memory pooling, we're going to eat up a big chunk of memory before we even run the game, okay? So that's one of the downsides of memory pooling, is that we're going to eat up all the memory we'll ever need right at the start. But we'll trade that for running time. And as we'll see, and I've said this before in the course, computer science and programming and software engineering and speed is all about trade-offs. It's trading memory for speed a lot of the time. So are you more concerned with memory? Are you more concerned with running speed? Okay. So who out there has heard of cache coherency or had to worry about that in their programming so far? Writing cache-friendly code is one of the most important speed optimizations in practice in your program. When data is fetched from RAM, surrounding values in the RAM are fetched and stored in what's called the cache, okay? So the cache is a very small part of memory. So for example, there's different types of cache. We're not going to get into L1, L2, whatever. But the fastest cache in RAM that we're worried about is something like 64 bytes or something like that. It's super, super small, okay? And so what's going to happen is when you fetch, say, an integer out of an array, you're not just looking up and grabbing that integer. You're grabbing that integer and the next 64 bytes, for example. I'm using 64 bytes as an example here, but it could be different on different processors, right? There could be way more or way less, who knows? Cache memory is faster, it's physically closer to the chip, okay, but is much smaller than normal RAM. And when I say physically closer, like the cache memory is on the CPU itself. And when we get down to really optimizing stuff, the speed of electricity, so the speed of light going from like your RAM slot through the RAM connection, through the motherboard to the CPU, that starts to matter, okay? So you want things to be in cache so that you no longer have to travel that like 6 inches across your motherboard to get to the RAM. That's how important this stuff is. So organizing frequently used data contiguously allows us to cache, allows our cache to fetch more of it on each lookup. And so what that means is we want to organize the data that we are storing in our program so that it is, if it's frequently used together, then we want it to be stored contiguously in memory, okay? And I'll get into, I have visual examples of all of this. So when we look up something, when we look up a value, and that value is not in the cache, then we call that a cache miss, okay? So if you talk about cache, if you ever heard of cache hits or cache misses, if we look up a value and it's in the cache, that's called a cache hit. If we look up a value and it's not in the cache, it's called a cache miss. Cache misses are very expensive. You don't even think about this. If you haven't gone to look up this on your own and you've been programming for 4 years now in computer science, you probably had no idea that this was even a thing, okay? Because I certainly didn't. Like, this is the curse of knowledge, right? It's that you don't know something until you know it. And so you've operated very, very contently this whole time, programming things, wondering why some things were fast, wondering why some things were slow, and it may have been cache misses. And you don't even know that until now. So cache misses are super expensive. So here's just an example for you. If we look up, say, an integer in an array, and that's not in the cache, looking up the value takes 200 clock cycles on your CPU, or 200 CPU cycles, okay? That's approximate. Multiplication takes 3 cycles. So you might have been thinking this whole time that, you know, if you eliminate, we have fewer multiplications, fewer additions, fewer subtractions, then that's how you optimize your program. You could do 65 multiplications in the same time it takes you to just look up the value that you want to multiply if it's not cached. Okay? So little did you know, when you said array I equals array I plus 1 times 3, those array I, that's 65 times more expensive than the multiplication. It's crazy. It's absolutely crazy. And here is a real world example of that. And you can run this, and it's mind blowing that this actually works. Okay? So here's an example. Here's an example here. So we have an integer array, and we've set up a new int array, and this is going to be 64 megabytes. Okay, so we've got 1024 times 1024, so that's a megabyte times 64. So we've got 64 megabytes of integers. Okay, here is loop number 1. Loop number 1, we're going to start at I equals 0. We're going to go through to the end of the array, and we're going to increment our counter by 1 each time. And what we're going to do is just go through the array and multiply each index of the array by 3. Okay, that's it. We go through the entire array, we multiply everything in the array by 3, and store it back in the same place. The second loop is going to do the same thing, except instead of doing it for everything in the array, you're just going to do it for every 16th value in the array. Okay? So this loop is going to do 16 times less work than this loop, right? Because look at this. This is I plus equals 16, and this is I plus plus. So this one is doing 1/16 the work of this one, right? We are literally doing 16 times fewer multiplications. And I know I'm repeating myself, but that's a very important point. Loop 2 does 6% of the work as loop 1, but it takes the exact same amount of time. If you actually run this program, loop 2 and loop 1 take an almost identical amount of time, even though it does 1/16 the work. Now, how does computer science explain that, right? This should take 1/16 the time. That's what we've been told. Our whole life up to this point is a goddamn lie. I just banged my desk, but it's been a lie. And it's because of cache coherency. And you didn't know how long it took to look up stuff. It sucks. So here's a graph for you. And this graph will blow your mind. Okay? This graph, down here on the bottom, we have that value of k. So this is the amount of time in milliseconds for that program that we just showed. Okay? If we say I plus equals k here, so 16 is the k for loop 2, k is equal to 1 for loop 1, right? So we're incrementing the loop counter by k equal to 1, implementing the loop counter by k equal to 16. So, look at this. The amount of time it takes for this to run is the same for all values of k up to 16. Even though, this one is doing half the work of this one is doing half the work of this one is doing half the work of this one, and this one is doing half the work of that one. But they all take the same amount of time. It's only after we increase our k value above 16 that our program actually starts to run faster. Why? Why is that? Well, it's the following. In this example, memory access dominates the running time. So the cache is going to grab 64 bytes at a time. And it just turns out that 64 bytes is equal to 16 integers, right? Each integer is 4 bytes. 16 times 4 is 64. So loop 1 has one normal lookup and then 15 cached lookups. And cached lookups, they're basically free. It's like a cycle or two, right? Loop 2 has one normal lookup, but 1/16 of them. And so it's a similar memory access time. And it turns out that these multiplications are pipelined. I don't know if you talked about pipelining in your architecture course, but it turns out that these multiplications, they're all just paralleled. Like the CPU just does all them at the same time. It's no problem. And so what's happening here is every time we fetch for k equal to 1 in loop 1, we are actually, the cache is grabbing the next 15 things as well. So it's getting 16 things. And so every memory access up until this gets to the next multiple of 16 is free. However, down here, every time we look something up, it's a cache miss, right? And so one cache miss is equal to, one cache miss followed by a bunch of cache hits is essentially the same thing as one cache miss. So what we see here is that this program will take about the same time to run if our k value means that we can get all the data in one cache hit. And that's why this graph is as it is. And it's only as we start getting into, for example, k equal to 32, where we're actually doing about half the work of k equal to 16. And then k equals 64, we're actually doing half the work. And that's because we're multiplying far few numbers and we don't need to worry about those. Or those cache misses. Yeah, well, I've already explained that. It's because of the cache misses. And yeah, it's crazy how those multiplications have almost nothing to do with the running time of this program. And so that may have been the first time you ever encountered something like this, and it's just crazy. Okay. Here are some more caching examples. So there's an entire gallery of processor caching effects. I highly recommend going and reading these. We don't have an exam in this course, but if you care about fast code, please go look at that. And also, Mike Acton, who is an amazing low-level video game programmer, had this great CPPCon talk about data-oriented design and C++, and this is all about writing cache-friendly C++ code, and this is the YouTube URL for that. So please go check out those videos, and if you don't have time to write those down, take a screenshot or whatever. So I'll leave that there for 1 second if you want to take a screenshot of those URLs. Okay. So how can we write cache-friendly data structures? And what this means is that we want to write our data structures such that as much of the data that we care about as possible is going to be in the cache. And not only that, but as little of the data that we don't care about is not taking up room in the cache. Okay? So for example, if we want to grab if we're grabbing an integer, ideally what we're doing is also grabbing the next few integers that we want to deal with. We're not grabbing like an integer and then some boolean that we don't even care about, right? So in order to avoid cache misses, we have to store data contiguously in memory. And again, contiguously means like one right after another in the actual physical RAM itself. So arrays and vectors do this. By default, an array or a vector stores data contiguously. But lists, sets, maps, dictionaries, those may not store data contiguously whatsoever. So for example, linked lists often use pointers to heap allocated memory, which is very slow. And so here is pretty much a rule for you. Never use a linked list. At least not in C++, right? Linked lists are garbage. Never use one. You go through computer science and you took an exam where you said that like the insertion time of a linked list is better than the insertion time of an array, and therefore in certain situations you may want to use a linked. No. Never use the linked list unless you have somehow magically coded up to be contiguous memory. Okay? And there are some linked list implementations that are inside a vector or whatever. But linked lists are storing pointers to heap memory. And so every single time you go to the next thing in a linked list, it's a cache miss because you don't know where that pointer is in memory, okay? And pretty much you can almost guarantee that any time you look up a pointer value and dereference it, it's going to be a cache miss, okay? Because you have no idea where when malloc got you that memory, it could live over here, it could live over here. You don't have no idea where it lives. And so it's not guaranteed to be contiguous. And so if you're ever looking up something by a reference or by a pointer, it's pretty much going to be a cache miss. So use a vector or an array wherever possible. If your data structure is large, if you have large data that you're storing inside a vector, then you may have to store pointers. That's just all you can do, right? However, that's not always the case, and we'll see how that's going to work. So here's a note on vectors. A vector is a dynamically sized array. When a vector, so this is another thing about vectors. This is a side note. This is not to do with cache misses. I just wanted to make sure that you know this going forward in your computer science careers. A vector is a dynamically sized array. When a vector is filled, it will create a new, larger temporary array and copy everything over. So what does that mean? Well, vectors aren't magic, right? They can't just magically allocate stuff. So what a vector will do, let's say we have a vector and we've said like, okay, give me a new vector. Maybe it's going to have some initial capacity, okay? So there's a few variables relating to vectors. One is their size. That's the current number of elements that you've inserted. But another property on a vector is its current capacity. And the capacity is the overall size of the array which it is internally storing. So for example, if I make a new array, or if I make a new vector, let's say that its internal array, well, it has to have some initial size, right? So let's say that initial size is equal to 4, or its initial capacity. So the underlying array inside the vector has a capacity of 4. And that means that I can put 4 things into this vector. So let's say I do that, right? I'm going to put a 1, I'm going to put a 3, I'm going to put a 7, and I'm going to put a 6, okay? Now, let's say I try to add an 8 to this vector. Well, the underlying capacity of the vector was not big enough. And so what happens internally is that the vector has to create a new array, and typically what it will do is create an array that's maybe double the size of the previous array. Okay? And then it has to copy each of these elements into the new one. So it goes 1, 3, 7, 6, and then it will insert the 8 into here. Okay? So however many elements we have in the vector, that is the size. And whatever the underlying size, whatever the underlying array's actual size is, right, the capacity, that's the capacity of the array, of the vector, okay? In C++, you have direct control over all of these variables. I don't think in Java you can actually modify the underlying capacity. So, what can you do? Oh, and the whole point here is that this is very slow. Whenever you have to resize that underlying vector, the underlying array inside the vector, well, vector does that for you. So you're hidden from all that. You don't know any of that's going on, but it is slow, right? So if I add 1,000 elements to a vector, what may be happening underneath is that that vector has had to resize itself like 10 times. And every time it resizes, it has to copy all the data over. And that's really slow. So what we can do, pretty much any time you ever allocate a vector that's going to be storing a lot of things in it, what you want to do is use the reserve function. So to try and avoid or minimize the amount of vector resizings, we can reserve an amount of space equal to some maximum size. So let's say, for example, I know that my vector is going to store at most 1,000 elements, okay? So, because I've done some analysis on my program or whatever. So what I can do is immediately after creating the vector, I can say vector.reserve however many maximum elements I have. And what that reserve keyword does is when it initially creates the array, instead of it being size 4 or whatever small value it gave, it will create that initial array to be of size max elements. So if you said it's 1,000, then the capacity of the underlying array in the vector will initially be 1,000. And yes, it's using more memory than it has to, but what you're doing in reserving like that is that whenever you insert now, you will not have any vector resizes until you actually get to the 1,000th element, and then it will have to resize, okay? And it uses a single malloc, and all the RAM is used immediately, and it's all contiguous. And so inserts into the vector won't resize it until the size is greater than max elements. So reserving space is really good. Someone asked, so reserving space in a vector is essentially memory pooling. So the concept of memory pooling has more syntax on top of that. So I would say kind of, but not really, okay? What it is you are reserving space so that you don't have to reallocate or resize the array. But that in itself is not exactly memory pooling. The process of memory pooling is more complex, and we'll see an example of memory pooling later. So, another thing that we have to consider when we're storing data inside a vector. So, for example, we're storing entities inside a vector, right? Is what data do we actually store? Okay, so one option is to store raw data inside the vector contiguously. Well, what does that mean? So storing the raw data in the vector makes it contiguous. So for example, if we have a bunch of integers, right? So if I have data here and I have a bunch of integers like 3, 7, 4, 9, then if I store the raw data, and in this example, the raw data is an integer, but maybe in your example, the raw data is an entity, something bigger, something smaller, it makes it contiguous, right? So these things are in memory right next to each other, these values. The data is larger, but more expensive to copy. So for example, if I was storing entities in here, if these were all entities, then let's say if my entity took up, I don't know, a kilobyte of space, then yes, they would be contiguous in memory, but if my cache size is less than a kilobyte, then it doesn't matter that they're contiguous in memory, right? Because my cache isn't going to be getting them all anyway. So the larger your data becomes, the less you care about storing raw data contiguously. So another example then would be to store pointers to data inside the vector. So storing pointers means that the data itself is no longer contiguous. However, pointers are easier to copy, but they're not cache friendly. So if we are storing, so what we're doing right now in our game engine up until this point is inside our vector, we have shared pointers to entities. And so basically every time we look up an entity, it's a cache miss, right? Because what we actually have is we have a vector like this. Each of these is a pointer. Oh, Jesus, I can't draw these asterisks. Right? So when we look up something, it's a pointer. The cache might get the next few pointers, but it's just caching the pointers. It's not caching the data. This pointer points to data out here in the heap memory somewhere, and that data is not being cached, right? So it's a trade-off. Do we store pointers or do we store data? Right now we're storing pointers because it was sort of the easiest thing to do, right? Can we do better? I don't know. We'll see as the lecture goes on. So right now the entity manager has a vector of pointers, and it's actually shared pointers, but shared pointers is essentially the same thing. So now every time we get an entity, we have a cache miss. Okay, so let's look at what this actually looks like. So let's say we have some data, and our data is larger than a pointer, for example. So let's say here we have the size of a cache hit right here. So what this means is whenever we look up this data, right, in an array, so this is going to be a vector of data, of raw data. Whenever we look up this data, the first bit of data, this is the cache size. So we might get this data and this data in the cache, okay? So then when we go to look up this data, we have a cache hit. When we then go to look up this data, we have a cache miss because this data was not in this cache. But when we look up this data, now this data goes in the cache. So when we look here, we have a cache hit. So in this structure, if we can align our data like this, every second lookup will be a cache hit. And that's okay, right? But in practice, our entities are going to be much bigger than a cache line, right? Because the cache might be 64 bytes, but our entity might be a couple of hundred bytes. So, relating to what I was saying before, if instead we store pointers in our vector, then whenever we look up a pointer, the other pointer values get cached, but not the data that they're pointing to, right? So let's say over here, this is our RAM, okay? This pointer might point over here, this one might point down here, this one might point here, and this one might point here. And so whenever we get this pointer, we look up the value, we dereference that pointer, and so what we do is we get this much in the cache, right? And so does this contain any of these? No, it doesn't. And so the next time we look up another one, we get another cache miss. And so now we look up this over here. Okay, well, this cache gets this much. And so you're always cache missing when you store pointers. So can we somehow, we've got this sort of double-edged sword here where our entity data might be of this size, right? So if this is our entity, in our ECS, if our entity is bigger than our cache line, how can we ever hope to get cache coherency when we look up entity data? Well, it looks like if pointers give us cache misses and the data's bigger than and the entity's bigger than the cache, how can we possibly do this? Okay? Well, let's look forward and we'll see how we do that at the end of this lecture. Okay. So, ECS and caching. Look down here for a second. What we have, our entity, is actually composed of a bunch of different components, right? So our entity is component 1, component 2, component 3, component 4. So entities are just containers for components. Currently, our entities store standard tuples of components, and standard tuples stores everything contiguously. So yes, an entity is a container for components, but at the very least, these components are contiguous, okay? So, if all the entity components fit within the cache line, then the entire entity will be cached for use. So that's good, because for example, if we look up an entity, and then we look up the first component, and we do something with it, and then we look up the second component of the same entity, that second component might be in the cache, and so we don't get a cache miss. And then when we look up the third component, well, that might be a cache hit as well. And so that's pretty good. Like, if the entire entity fits within the cache and all this is contiguous, then if we do something with component 1, then do something with component 2, then do something with component 3, then do something, like, none of those are cache misses. So that's at least somewhat of a benefit. But is that actually what we want? In practice, is that how we are using entities? See, when it comes to designing how your memory is laid out, it's not only like the intuition behind, like, for example, an entity as a container of components. What matters even more is actually how we are using the data within that entity. So let's go forward. Entities and caching. So here, for example, let's say we have a contiguous string of entities, and we have the cache. So let's say that an entity, our cache line could fit 2 entities into it. So if entities themselves, like the raw data of an entity, is stored in a vector, they are contiguous. The cache could potentially load multiple entities, but only if the entities are really small. And so, you know, in practice, your game is going to have kind of largish entities, right? Because you're going to want to have a bunch of components with a bunch of data in each component. So, but what we currently do is we store a shared pointer to an entity, right? So these are all shared pointers, but we're gonna pretend that we're not doing this for now. We're gonna pretend that we are storing the raw entities within the vector. Okay, so here, if we look at this, so if we're gonna take this view right now of one cache line and one entity and another entity, and we're gonna zoom in on this. Okay, so let's zoom in on it. So here is that view, but zoomed in. So what we actually have, if we look at the entity number 1, because we're storing a tuple of the components, right? We actually have component number 1 stored contiguously with component number 2, component number 3, and component number 4. And I've color-coded them just so you can see the difference. And all of these got cached. And then we have entity number 2's component 1, component 2, component 3, component 4, right? So the entities are stored contiguously, but the components of the components are stored contiguously, but it's all the different components. Components of the same type are not stored contiguously. Why would that matter? Do we want our memory to be laid out like this? Why would that matter? Okay, let's look into why that matters. Storing entities contiguously makes intuitive sense, right? Since the cache could potentially now fetch multiple entities. However, caching is all about access, the patterns in which we access the data. How it's stored is very important, and our intuition is very important, but it's really all about how we access the data. And so how we want to access the data inside the entities determines how we should actually store those entities. So let's look at some examples of the systems that we use in our game engine. Because if we do an analysis of the systems, that shows us our access patterns of the data within the entities. Okay? All right. So let's look at our movement system. Our movement system does something like this. For every entity, get the transform position, get the transform component, add the velocity to the position. Oh. So it looked like in the movement system, all we really care about is the transform component. Okay, let's go down and look at rendering. In rendering, all we do is we care about the animation sprite, and we just draw that to the screen, right? Maybe we care about the transform component as well. In the collision system, we're just getting the bounding box, and we're getting the transform. We don't care about the sprite. We don't care about the lifespan. We don't care about any of that stuff, right? So if we look at this now, we look at the access patterns of the data inside the entities. Well, in the movement system, we only cared about one transform, or one component. In another system, we may only care about another component. And in another system, we may only care about one or two components. However, but the main point here is that very rarely is a single system looping through all the entities and accessing all the different components. Okay? Very rarely is that actually happening. And so ECS systems usually only access one or two, or at least very few, different types of components of each entity that they're operating on. And so given this access pattern, what we actually want to do is we would want the cache to store similar components rather than entire entities. Okay? Components are small, so the cache line could fit many more components than it could fit entities. So this is what we've seen so far, right? This is what I just talked about, where this is storing the entire entity contiguously. And so what happens is, if we look up the transform component of this entity, well, the cache then gets filled with all this garbage about like the animation and the lifespan and the hit points that we don't care about right now. Wouldn't it be great if we could get all the transforms instead of all this garbage data that's filling up the cache line? And so ideally, this is what we want to have, okay? So in one cache line, we might be able to get the first component of each of the entities, right? And so that way, when we're looping through the entities and we're just looking at this single component, well, we've gotten like the next few of them in the cache for free. And so ECS systems operate on similar components. And if the components are contiguous, we get more cache hits. But how can we achieve that, right? So our entities store all the components. So how could we possibly split that up? We can't split up our entities like, oh my God, how are we going to do that? How do we achieve that? Well, what we're going to do is something called memory pooling. And memory pooling is going to accomplish two things for us. It's going to accomplish the elimination of dynamic memory allocations, and it's also going to accomplish a really neat storage method to allow us to store components contiguously instead of entities contiguously, and then we can really easily look up and find all that data as well. So it's really exciting because it's going to solve like a bunch of problems at once. So a memory pool, think of a big swimming pool of memory. That's what it is, right? So instead of like every time you want to store a new object, you go and dig a small hole and put it in that hole. That's the heap. That's a malloc call. At the very beginning of your program, you dig a big swimming pool and you just throw things in there. Okay, so that's the memory pool. It's a pre-allocated chunk of memory that will be used for the storage of data of a given type. So for example, entities or whatever. By pre-allocating the space, we don't need to use dynamic memory allocation. However, we may need to know a maximum size beforehand. So for example, you could say, I'm only ever going to have 10,000 entities, and so my memory pool is going to be of size 10,000. Or so the memory will be the size of an entity times 10,000. Okay, so here's what our memory pool is going to look like. I'm representing it as a table, okay? So the first memory pooling scheme is the first one we talked about, where we're going to have essentially this memory pool, we're going to say pre-allocate a vector of size 10,000, for example, and inside that vector, we're going to store raw entities, okay? And so inside the entity, the data for the components, like the data for that entire entity is contiguous. So here, what we see is an example of that, where an entity is going to be a column in this table, okay? So one entity, for example, this first entity, entity 0, here's the first component, right here. Here's the second component, here's the third component, and here's the fourth component. And so if you look, this is going to be a big vector, right, of entities, and here's where the first entity is, here's where the second entity is, here's where the third entity is. And each entity here is represented by one column in this table. Okay, so let's add another entity to this table. That's how we go. And then we keep adding entities to that table, okay? So again, the important thing to realize here is that every entity, this is a vector. So you can think of the first row here. This is the vector of entities. And each column is the contiguous data of the memory. Sorry, I want to change the ink color to black. Okay, so the way that this data is laid out in memory is that this one comes first, then it's this one, then it's this one, then it's this one. So these are contiguous. Now, because they're laid out in that order, next would come this one, then 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 this one, right? So we've got one entity, then the next, then the next, then the next. So this is the vector of entities approach to memory pooling. So this memory pool could eliminate all dynamic memory allocations by being big enough to fit all the entities. And so we're going to trade upfront memory for runtime speed. And let me get rid of this these ink notes here. So what this means is, we've got this huge array with enough space for all our entities, and all we ever have to do when we want to add another entity is just put it in the next free spot. We don't need to call malloc because we've already got this huge memory pool allocated for us. So that completely eliminates the need for any dynamic memory allocations just by having this huge vector pre-allocated. So we're trading upfront memory cost for runtime speed. And it works really, really well for known hardware, but also for unknown hardware. When the new entity is created, we need to find an empty spot for it in the table, right? So in our memory pool. But this is much faster than malloc in practice. So for example, just scan left to right for available space. Whenever an entity dies, we mark it as available. And we also save time by not deleting dead entities. And I'll get to a visual example of that in a second. Okay. Here's how we solve that second problem, where we want components to be contiguous rather than entities being contiguous. Okay, so how do we do that? Instead of storing vectors of entities, what we're going to do is we're instead going to have a vector for each component type. So instead of the columns which were entities being contiguous, we're going to change it so now that the rows or the components are contiguous. Okay. So now what we have is, instead of a vector of entities in which the columns or entities are contiguous, now each row is going to be a single vector of just that component type. So each row is a vector of component, whatever that component is, whether it's the transform or the lifespan or whatever. And so all of that component is now contiguous. Now what we can do is how do we access that memory? If we've got now like a vector of C1s, a vector of C2s, a vector of C3s, well, how the hell do I know where the transform component of my entity is? Because my data is no longer living in an entity. The entity is no longer a container. The data is living in a memory pool. Right? So how do I arrange all that? Oh my God, I don't know. Well, each entity ID, we can use that as the index into the vector. It's so simple, right? So for example, if I want to get the lifespan component of entity 0, well, all I have to do is have some sort of function which knows where the lifespan vector is and look up element 0. See that? So entities essentially just become indexes into this huge array or memory pool. And so now we have a memory pooling solution, but we also have components stored contiguously. Crazy. Okay, so entity as an index. So the entity class will no longer actually store components as member data. We're throwing all that out, okay? The entity will only hold an integer index. That's it. And that integer index is going to tell it where its associated data lives in the memory pool. So entity functions will now access our memory pool and look up the data in the associated index. So no longer do we have data living in the entity, right? We have data living in a memory pool. And so the functions on entity are no longer grabbing its member variables. They're grabbing data from the memory pool. Someone just asked, how would this work if not every entity has every component? That's a good question. We're going to see how that works, but essentially, every entity already has every component, right? If you think about it, the standard tuple that we're currently using, it has a default constructed component, but what we do is, inside our component base class, if maybe you're not in the class or you don't remember, but each component actually does exist. However, each component has a Boolean which says whether or not the entity currently has this component. Okay? And I'll show a visual example of how this works, and it'll all work. But how the hell do we implement that? Okay. So, here's how the hell we implement that. Our memory pool is going to have a tuple of vectors of components. Okay? So, if we have 4 different component types, how this will look is, so currently what we have is we have an entity has tuples of components. We want to move away from that. So an entity has tuples of components, and then we have a vector of entities. So rather than having that, what we're going to have is multiple vectors, each only storing a particular component type. That's going to be called our entity component vector tuple. So it's an entity component vector, and that's a tuple storing the entity component vectors. Okay, so now inside the memory pool, we're going to initialize this data structure called entity component vector tuple, and we're going to call that data, right? We'll just call it data. It's our big memory pool data. And then if we want to get, for example, let's say we want to get at the vector component 3. So the easiest way we can do that, it's super easy. We do it just the same way we've been doing it before, except now we have to call standard vector. So this, in order to get the variable from inside the tuple, we can use standard get with the type. Well, the type of component 3 is just standard vector component 3, so we pass that in, right? So if we want to get an entity's component type t, we can just say standard get standard vector t data, right? We pass that variable in, and then this returns the vector. But how do we know where this entity's component is stored? Well, it's at the index of the entity ID. C++ handles it all for us. It's done. It's done. Crazy. Okay, so let's look at the memory pool. There's a couple of other things that were stored inside an entity, remember? There was a tag, and there was an active Boolean or not. So every entity has a tag, every entity has an active, and every entity also has components, right? So what we do is, we're going to take all the tags and all the Booleans of whether or not they're active and create their own vectors as well, okay? So the entity memory pool is going to store the following data. We're going to store the number of entities that we have. That's an important thing to keep track of. We're going to store the entity component vector tuple, and we'll call this the pool, right? So this is the pool of components. But we're also going to have a vector of strings. That's going to be the memory pool for the tags. And we're going to have a standard vector Boolean, which is the memory pool for the Booleans of whether or not things are active. So we have entity memory pool, and we're going to pass in, when we construct the entity memory pool, we're going to construct based on some number of max entities. If that's 10,000 or 5,000 or 200 or whatever we want to pass it in. Okay. We're also going to make this memory pool a singleton. So who out there in the chat has heard of a singleton design pattern before? I haven't actually covered singleton in this class yet. So without going too deep into it, a singleton essentially just, it's a design pattern that ensures that only one instance of a given class can ever exist. Okay? And exactly. So someone said a class can only be instantiated once. So if we're talking about something as large and important as a memory pool, we only ever want there to be one memory pool. Okay? So we're going to make it a singleton class. And the way we do that in C++ is magically simple, okay? So what we do is we're going to create a static function on the entity memory pool class, and that static function is going to be called in order to get access to the single instance of this singleton class. So this static function is going to return a reference to the instance of entity memory pool, and the way we do that is as follows. So we're going to, inside this static function, create a static entity memory pool variable called pool, and we will set it up to be of length max entities. Now, whenever you have a static variable allocated in a function, that line of code is only ever actually run the first time you call that function. So this line number 10, will only ever be called the first time you create it. So the first time you say, hey, give me the instance of entity memory pool, it will set up the memory pool. And then from then on, the only line of code that will ever be run is returning the instance reference, okay? So this is all you need to do to create it. Oh, and we also make the constructor private. So that way, nobody can construct an entity memory pool. If the constructor is private, it can't be constructed anywhere except from within its own functions. Okay? So now, whenever we want to access the entity memory pool, we call entity memory pool : instance. It will set it up, and it's a singleton, so we know we're accessing the same thing. And the cool thing about this is that the data lives very safely within this function. It's not accessible globally. However, this function is accessible globally. And so with this design pattern, we're ensuring in C++ that we have global access to our singleton entity memory pool, which is awesome. All we have to do in order to get access to this is include entityMemoryPool.h in our file. Okay, so then inside our entity memory pool, we're going to have various functions for getting at that data, right? So for example, we have getComponent and we have getTag. So in order to get the component of a given entity, well, we need to be passed in the entity ID. And so in order to get a reference to the component for the given entity, we're going to return standard get, standard vector t from the data, right, of entity ID. Oh, sorry, instead of mdata, that should be mpool. But we just look it up in the tuple. It's like this, it couldn't be easier. C++'s tuples are just great. And we know that that vector is going to store things contiguously. If we want to get at the tag of a particular entity ID, then all we have to do is return the tags vector indexed at the entity ID. That's it. And now we have to change the entity class. And look, our entity class now is literally just an integer. It's a wrapper around an integer with some helper functions to allow us to get the data. So for example, before, in order to get the component of a given type from an entity, right, I was looking up the tuple that was stored inside the entity. But now we're no longer storing it that way. We actually have to go to the memory pool, right, because it's no longer living in the entity. So here, in order to get the component of a given type, get component, oh, my cat is walking around my legs. We just return entity memory pool, the instance of it, right? So this is how we get the singleton entity memory pool, and we call its get component function of the given type with the ID. Done. If we want to get whether or not it has component, we just call the same thing on the has component function, which looks it up by ID. It's done. It's crazy. So that's how we implement this, is we have the entity memory pool be a singleton that we can access from within the entity class. Now, this is not the only way to do it. It's just the way that I've seen to do it. Okay. So now in the entity manager class, right, we're no... My cat is crying. Just give me 1 second. Freckles is here. He wants to learn more about entity memory pools. Sorry to interrupt the lecture. You can't ignore the kitty forever, right? Okay. So, back to this. Now we have to change the entity manager class as well. So the entity manager, whenever it adds an entity, well, before, all it did was it said, hey, put a new entity into its vector of shared pointer of entities. But now we have a memory pool, right? So what we have to do is one more change to the add entity function of the entity manager class. And what this does is it has to call the entity memory pool instance, and it has to call its function. Okay? And then it just pushes it back. And now we no longer have to store shared pointers to entities because entities are only integers. So we can just pass entities by value all over the place. Oh my God, it's so beautiful. It's so beautiful. It solves all our problems, right? Entity is now just this tiny thing that we can pass around. We don't have to have shared pointers anymore. It's all contiguous by component type, and it's all really fast lookup. Oh my God, it's so good. Okay. So now in the entity memory pool, we have to have one more function, and that's how do we actually add the entity to our pool. So whenever we want to add an entity of a given tag, what we have to do is we have to first, a really important step, is look up the next available entity index in the memory pool. Okay? So that get next entity index, I'll show you how we can do that in a second, but however you do that is going to be a lot simpler than malloc. And you have to set all the vector indexes to 0, and you have to set the tag and the index to the defaults, okay? So no longer do we have a single entity constructor that sets all of its values to the default. So in here, unfortunately, the only annoying thing is we have to go through each of the vectors at that index and just set them all to the default values, okay? But that's not so bad. It's just one little annoying function that we have to write. All right. So the ECS memory pool. Whenever we create the memory pool, we're going to have many copies of a blank default constructed component of each type, right? Because we're setting up the memory pool. It has room for every component. It's going to set them all up with the default constructor. And so we recall that every component has a Boolean associated with whether or not a given entity actually contains that component. And so the entity also has this active Boolean to say whether or not the entity is currently active. So here is what we're going to see kind of in practice, okay? Here's what our entity memory pool is going to look like. We're going to have each entity, right, each entity index be the index into the vector of these components. So this is a vector of C1s. This is a vector of C2s. This is a vector of C3s. This is the vector of all the tags, and this is a vector of all the active Booleans, right? So if we go back and we look at the entity memory pool, we see here we have the vectors of all the components, the vector of all the tags, and the vectors of all the Booleans. And here's just that drawn out, right? So when we put a new entity into the memory pool, we need to find a location for it within the memory pool. And so what we're going to do, naively, is just the simplest possible thing, which is scan from the beginning of the pool all the way to the end of the pool and find the first location of a non-active entity, and we'll use that slot. Okay? So here we'll do an example step by step of what that looks like inside the memory pool. So here we have all of our components. Our components initially, so let's say that they have some data, okay? So our components here are going to have some integer data, and they're also going to have the Boolean saying whether or not the entity actually contains that component. So by default, the entity contains no components, and so all the components' Boolean variables are going to be set to false. The tag is going to be set to an empty string, and the active Boolean is going to be set to false. Because this entity, none of these entities are active yet. These are all blank entities just waiting to be filled up. Okay, so let's add an entity and see what happens. So we're going to call entity P equals entitymanager.addEntityP, okay? So what we did was we scanned from left to right and we found the first index where active was set to false. And if active is set to false, it means that that entity no longer exists, so we can take over that slot. So what we did was we took over the slot, we default constructed all of these things, and then we added the tag in. So the tag is now P, and we set, hey, this entity is now active. So we set that to true. Now what we do is we set, let's say we want to add component C1 to this entity. Okay? Well, what we're essentially just doing is we're constructing C1 and we're setting it to true. So now this entity has a C1 component, but it doesn't have a C2 and it doesn't have a C3. Now, let's set the value of the component C1 equal to 7. And so what we did was now we just have a value of 7 here. Okay? See how like easy this is? This is what it's doing under the hood. Oh, 1 second. So I just had a ferret run into the room around my legs and then run out again, and I couldn't catch them in time. 1 second. Oh, I'm interrupting again. Here we go. Ugh. This is much more interesting than the lecture. Okay, I'll let them play. I'm like 3 minutes from the end of this lecture. Okay. That was Flash and Luna, by the way. Flash is the ferret. Oh, jeez. So what we saw is like how easy this is to like, oh, jeez. Hang on. You don't want to see my face anymore. Oh, that's the wrong one. Here we go. Okay. So now let's add another entity to that. And after I'm done the lecture, I'll go get the cats again. So, here we go. This will start working again. Now let's add another entity, and we'll call this one Q. Okay? I will answer all the pet-related questions once I'm done, because I'm almost done this lecture. Let me get through it, because I'm already over time. So we added another entity, which was Q, and so what we did is we just scanned through until we found a false, and we put it in there, right? Now we're going to add component C2, and so up here you see the Boolean of C2 is set to true for E1. Then we're going to set its value equal to 3. And now what I'm going to do is I'm going to actually remove component C2 from E1. And all that I do in order to remove the component is set the value equal to false. I don't even need to touch the value. I just need to set the Boolean to false. Because whatever the value here, because I don't have the component, my systems will not be accessing that value. So if I remove components, I don't even need to default construct the whole thing anymore. So I'm saving time even on that level. Okay. So here's where we are right now. Let's say we want to destroy an entity. Okay. Let's say I want to destroy the entity P. All I need to do is set active to false. That's it. Isn't that crazy? I don't need to delete any data. You saw what was happening with my cats right now. So then, since I destroyed this, the active became false. And so if I want to add another entity, I can take over this slot without actually deleting this data. All right. So now entity R is entitymanager.addR. I can take over this slot, default construct all the values, and that's where this entity now lives. Now, if I want to add the component C3, then this becomes true, etc., etc. Okay, Someone said components will still have several values, right? This dot value is just a placeholder example. Yes. So for example, this might be the transform component, and instead of just having one integer, this could have like position, previous position, speed, acceleration, all that kind of stuff, right? This could have like the lifespan and the frame created. This is just, I couldn't possibly fit all of that into a demonstration slide. So now if we go back and we look at our systems, the movement system is only accessing the transform component. And so look, when we get these, when we go through the movement system, we're getting all this data contiguously. When we go through the entities and we want to draw things, that's all we're doing. We're getting this contiguous data, right? So we've solved, and now some things will have more than one entity, or want more than one component, but that's fine. We're doing the best that we possibly can by using a system like this. And so what memory pooling did for us is it allowed us to have no dynamic memory allocations for adding new entities, for adding new components, for removing new components, or even deleting entities, right? Entities became indexes into this array, so entities are now smaller, they're easier to pass around, and there's no pointer dereferences whenever we access an entity. And also, we have all of our component data now contiguous, which is actually what we want because ECS systems pretty much rely on just a very few number of components rather than the entire entity. So I don't know about you, but I love this lecture because I think it's like an example of real world stuff that, and you know what the funny thing is? You could be in industry for 20 years and not even care about stuff like this. Like if you write code in Java, how are you going to do this? You don't have access like this to memory in Java, right? So if you're writing a game in Java, okay, you have a vector of objects. Do you know what an object is? It's a pointer. So every time you access an object in Java, it's a cache miss. Even if it's just a component, even if you're like you can't store the raw data of a component. Like you'd have to, I'm not saying you can't do this in something like Java or Python, but it would be much more difficult and you'd have to like have all these janky hack solutions and you couldn't use nice data structures and stuff. Like memory pooling is one of the most powerful tools that you can use in C++ game programming. Someone said, but you are limited to just a few entities, or am I wrong? No, you're limited. So for example, I said before that in order to use a memory pool, you need to know the maximum amount of entities in advance. That's not entirely true. Let's say that we knew we were only going to use 10,000 entities, right? So we created this table to be 10,000 entries long. Maybe it takes up half a gigabyte of memory, right? Maybe it takes up a gig of memory. Who cares? We have that amount of memory. But if we really wanted to save that memory, what we could do is have the memory pool be less than, maybe we want it to be like the average amount of entities. And then if we need to add another entity which is larger than the size of our memory pool, well then we could just use a little bit of processing time there and resize the memory pool. Now, ideally, we never want to resize the memory pool because it contains a ton of data, but it is possible to resize the memory pool. Okay, so what I'm going to do, I'm going to end this lecture here. Actually, let me just answer some of these questions. Is ECS a good idea when making a very specific game rather than a general purpose game engine? Someone told me that there are almost certainly better solutions when your game engine requirements are narrower. Thank you. So for example, if I was trying to make the game of chess, I wouldn't use ECS, right? But I think that as soon as your game has multiple levels, multiple types of NPCs, or multiple weapons or tile types, I immediately go to ECS. And so whoever just asked that question, if you type !playlist, you can go back to the introductory lectures for this course and see what ECS will afford you. We're way past that point in the course at this point. But yeah, go back and watch the lectures and then you can decide whether or not you want to use ECS or not. But in my opinion, as soon as your game is like more than one screen or more than one enemy type, you want to use ECS. You don't have to go all the way to memory pooling, not by a long shot. You can just go through and write the small engine that we wrote, and you can have. As soon as you see the power of ECS, you're not gonna want to go back to like hard-coded solutions, in my opinion. Okay, so that is the lecture. I'm gonna end the recording there for YouTube, but just give me a second. Don't leave the stream yet.